Hello and welcome once again to CM Educators with Mwalim Juma Ogutu. So today we are beginning on acids, bases and indicators. So we begin by saying that some of the foods that man eats are sour while others are bitter. So the sour taste is due to the presence of acids, whereas the bitter taste is due to the presence of bases. So many foods that we consume, they contain, some of them contain sour taste while others contain bitter taste. So we are saying that the presence of the sour taste is due to the acids, while the bitter is due to the bases. So example of substances that contain acids are fruits such as oranges, lemons, and sour milk. So such acids are referred to as organic acids. So we are saying that these fruits are we have oranges and lemons contain acids, and these acids now that are contained in the fruits and also in animal products, we are calling them organic acids. We are calling them organic acids, and other acids are formed from reaction of chemicals. These are called inorganic or mineral acids. They are called organic or mineral acids. Those that are formed from the reaction of chemicals are called inorganic or mineral acids. So inorganic acids are common in school laboratories. Example of substances that contain bases include antacid tablets and also wood ash solution. So using tests to clarify substances as acids or bases is not an accurate method, because now the acids that are made in laboratory, you cannot use using the tongue to test to see if they are acids, because some of them may react with the body parts, and some of them have corrosive effect, and so they may be harm to the body parts. So there are, however, certain substances which show different colors when in acids or bases. So other than testing using the tongue, we have some substances that we use that show different colors while in bases and acids, so that will help us to now clarify if a substance is an acid or a base, other than using the tongue to test whether it is an acid or a base. So we are saying that these substances show different colors when in acids or bases. Such substances are called indicators, and they are used to classify substances as either acids or bases. So we are saying we will be using indicators now to classify substances as either bases or acids. So let's look at the simple acid base indicators. Simple acid base indicator. So these simple acid base indicators are made from flower extracts. So an experiment we are carrying out now to see to it that can flower extract be used as an acid base indicator, or can flower extract be used as an acid base indicator. So the procedure that we have to follow is, the first one is that we crush the flower petals in using mortar and pestle. So the flower parts that we'll be using are the flower petals, so which are the one we are going to crush using a mortar and pestle, and add small amount of ethanol or propanol. So we add a small amount of propanol or ethanol, then we continue crushing until a deep colored solution of the extract is obtained. Until a deep colored of the extract is obtained. So we decant the extract into a beaker or a boiling tube. Then now we place 2 cubic centimeter of each of the following substances into separate test tube. So now we have these substances that we want to determine whether they are base or whether they are acids. So the substances that we have hydrochloric acid, we have sodium hydroxide, we have sulfuric acid, we have potassium hydroxide, we have lemon juice, orange juice, we also have lime water, wood ash, baking powder, and sugar. So we are saying so these are the substances that we want to determine whether they are acids or bases. So we add 2 to 3 drops of the flower extract into each test tube and classify the substance in the test tube as acids or bases. So now we are doing it separately for each and every substance. We are now adding 2 to 3 drops of the flour we are adding 2 to 3 drops of the flour extract into the tube and the test tube containing each of the substance. So now now we record our discussion, our observation. Then now we go ahead to see now what we observe and how we can explain it. So solutions of hydrochloric acid, sulfuric acid, orange juice and lemon juice give similar color changes with the same flour extract. Remember that we had just said that they'll give these simple indicators, simple flour extract indicators. They'll give a certain color in acid and a certain one in bases. So we are saying that for lemon juice, orange juice, hydrochloric acid and sulfuric acid, they'll give the same color using the same flour extract. Now meaning that the hydrochloric acid, sulfuric acid, lemon juice and orange juice, they belong to one group. They are either acids or bases, so they belong to one group. And remember that when we say that some of the food that we consume contain either acid or base, we gave an example of orange and lemon being an example of the food substances that contain acid. So now the color they are giving, it is unique, it is the same for hydrochloric acid, sulfuric acid, lemon juice and orange juice. Now all of the four are all acids. Then now lime water, solutions of sodium hydroxide, potassium hydroxide, wood ash and baking powder give a similar but different color. So we are saying also that lime water, sodium hydroxide, potassium hydroxide, wood ash and baking powder, they also give a similar color. They give a similar color. The one that is different from the one that has been given out by the sulfuric acid, hydrochloric acid, lemon juice and the orange juice and the lemon juice. So it is different from the ones that have been given for this group that contains lime water, sodium hydroxide, potassium hydroxide, wood ash and baking powder. So then we also had water and sugar solution that have no effect on the flour extract. So they are neutral. They are neutral. So the composition of the flour extract continuously changes with time, causing the color of the extract to change. Now this as we have, when you have already carried out the experiment, you realize that as time goes by, when this extract is left with the substance that we are testing, we will see that the color begins to change. The color begins to change as time goes by. So the mixture of the flour extract and acid or base also changes color with the time. So flour extract therefore give inconsistent results when used as an acid base indicator. So the flour extract, they give inconsistent results because at the beginning you will have another color and after some time it will change the color. So when freshly used, they'll give, when freshly used with the substance that now you are testing to classify if it is either a base or an acid, it will have, at the beginning it will have a different color, then after some times it will again give a different color. So we are saying that it gives an inconsistent result. It gives inconsistent results. So for the best results, flour extract should be used when freshly prepared. They should be used when freshly prepared. Then we make observation just when it has just been added to either the acid or the base, so that we come up we classify the substance that we have been testing. So other colored parts of the plants that may be used. So we not only use the flower petals, but other parts of the flower that are used Other parts of the flower may also be used, not only the flower petals. So the examples, you have the Tradescantia, and we have red cabbage, you have beetroot. They can also be used. So in the laboratory, we have commercial indicators which give more consistent results, which now we use them as acid-base indicators. So we have commercial indicators in the laboratory that will give us consistent results. So even if you work out the experiment, then leave it for some time, the colors won't change, they'll remain the same, which is a bit different to the flower extract that now changes as time goes by. So let's look at these commercial indicators and how now they are used, and now the colors that they give in a given substance, either base, acid, or in a neutral substance. So the experiment, what is observed when litmus solution is added to an acid, a base, or a neutral solution. So the procedure, we place 2 cubic centimeter of sodium hydroxide. We also have hydrochloric acid and water into separate test tubes. So you have three separate test tubes that now we are placing in 2 cubic centimeter of the substances. We have sodium hydroxide, hydrochloric acid, and water into separate test tubes. So then we add 2 drops of the litmus solution into each test tube, and then we record the observation. Remember, now we are adding 2 drops of the litmus solution, which is now our commercial indicator that we say that it will be consistent in its results. It will be consistent in its results. Then we make the observation. So let's discuss and see the observation that has been made. So litmus indicator is red in an acid. Litmus indicator is red in an acid, and it will remain to be red even if after having carried out the experiment, then we leave it for some time, it will still be red because they give consistent results. So it's red in an acid, blue in a base, and retain its purple color in a neutral solution. So you expect when a litmus solution is used as an indicator in any given substance, it will be red in an acid. When now we have a red color, it means that the substance is an acid. Blue, it will be a base. Then when it retains its purple color, it means that it is a neutral solution. So litmus indicator is one of the commonly used commercial acid-base indicator. So it's one of the commonly used acid-base indicator. So we not only have the litmus solution indicator, but we also have the litmus paper. That now there are 2. We have the one that is red and the one that is blue. So the one that is red, when placed in a solution that is a base, it will turn to be blue, and the one that is blue, when placed in a solution that is acidic, it will turn to be red. And when either red or blue is placed in a solution that is neutral, the red will retain its red color and the blue will retain its blue color. So we are saying that the indicator is also available in paper form as litmus paper. So other commercial acid-base indicators include, we have phenolphthalein, and you also have methyl orange. So we carry out an experiment to see what is observed when commercial indicators are added to different solutions. So remember, now we have seen the litmus solution, that of litmus solution. Then we go ahead to carry an experiment to see how the color changes for phenolphthalein indicator and methyl orange while in different solutions. So we take 3 test tubes and put 2 cubic centimeter of hydrochloric acid in each 3 test tubes. Then we put 2 cubic centimeter of hydrochloric acid. Remember, now in this case we are using hydrochloric acid in 3 different test tubes. Then we are saying to the first test tube we add 2 drops of litmus solution. To the second and third 2 drops of phenolphthalein indicator, and then methyl orange respectively. Then we record the observation that we make. So we repeat the same experiment using water and also lemon juice solution or suspensions of the solution. We also have the suspension of soap. We have wood ash, we have baking powder, we have antacid tablets, we have toothpaste, then we have sour milk, ammonia, ammonium sulfate, sodium chloride, sodium hydroxide, we have carbon dioxide, we have sulfur dioxide, we have sulfuric acid, we have nitric acid, we have calcium hydroxide, then magnesium oxide. So those are some of the substances that now will be carrying an experiment to determine how to classify them either as base, acid, or neutral solution or substances. So phenolphthalein indicator is colorless in acidic. Phenolphthalein indicator is colorless in acidic, pink in basic, and colorless in neutral. Remember, phenolphthalein indicator itself, it is colorless. So we are saying that it is giving a colorless. It's giving a color. It is a colorless in acid. So the indicator is colorless in acidic, pink in basic, and colorless in neutral. So when it is added in an acid, now we will have a colorless solution. We will have a colorless solution. When added to the base, it will have a pink solution. Then when added to a neutral solution, it will be colorless solution. Then you have methyl indicator that is pink in acidic, yellow in basic, and orange in neutral solution. So as the name suggests, it is methyl orange. Now this indicator is orange in color. So it is pink in acidic, it is yellow in basic, and orange in neutral solution. So the colors obtained when the indicators used in the experiment are added, the solution of various substances are shown in this table here. So you have the indicator, you have litmus, we have phenolphthalein, we have methyl orange. Then you have the color in an acid, in base, then in neutral. So litmus will give a red color in the acid, blue color in the base, then in neutral it will remain to be purple. Phenolphthalein is colorless in acidic, pink in basic, and neutral it is colorless. Then methyl orange is pink in acidic, basic it is yellow, then in neutral it is orange. So apart from the three commercial indicators used, phenolphthalein, litmus, and methyl orange, we also have a universal indicator that now has a pH scale. So as you have just seen that the three, they will only give the color change but won't show the strength of either the acid or the base. But for now, for the universal indicator and the pH scale, they'll give us the color and also show the strength of either the acid or the base. So the universal indicators and the pH scale. So the acid-base indicators discussed so far provide no information about the strength of an acid or a base. So some acids are strong while others are weak. This also applies to base. Some bases are strong and others are also weak. So likewise, bases are strong while others are weak. So the universal indicator is a mixture of several indicators. So we are saying that a universal indicator is a mixture of several indicators. So it exhibits a range of colors in acids and in bases depending on the strength of the solution. So now the color will change depending on the strength of the solution used, whether it is basic or acidic. So in a strong acid, it will give a different color as compared to a weak acid, and likewise also in base, it will give a different color in strong base and also in a weak base So these shades of colors are related to a continuous acid-base scale called the pH scale. So the colors we have a pH scale that has values that ranges from 0 to 14. So we have an experiment we have an experiment that now what are the pH values of some of the solution. What are the pH values of some of the solution? So we'll have some solution, then we carry out an experiment to see their pH values. So we place about 1 cubic centimeter of dilute sulfuric acid into a test tube. Then we add 1 drop of the universal indicator and observe the color of the solution. Then we place the test tube and its content against the pH chart and determine the pH value. So we also repeat the same experiment using distilled water, dilute solutions of ethanoic acid, we have lemon juice, we have nitric acid, we have hydrochloric acid, we have sodium chloride, we have sodium hydrogen carbonate, we have ammonia solutions, we have calcium hydroxide, I also have sodium hydroxide, wood ash solution, and soap solution. Using all those substances, we also carry out an experiment to see the color change, and then we compare them using the pH chart to determine now the pH value of each. So we discuss and see now some of the observation that has been made. So the pH values of acids ranges from 0 to values just less than 7. Values just less than 7. So the values less than 7, you have 6.9. So solutions of sulfuric acid, hydrochloric acid, and nitric acid have pH values which range between 0 to 4. So 0 to 4 are strong acids. 0 to 4 are now strong acids. Then you have lemon juice and then ethanoic acid. They have values which range between 4 and 7. And now from 4 to 7 we have weak acids. So from 7 to 0, as the pH values decrease, from 7 to 0, the strength of the acid increases. So the strength of the acid increases as now the pH values reduces from 7 to 0. As now the pH values reduces from 7 to 0. Then you have distilled water and sodium chloride solution. They have a pH of 7. Sodium chloride solution is just the table salt that we use. It is neutral, same as the distilled water. So not all water, not all the liquids water liquid have a pH of 7. We have some are acidic. Like for example, we have acidic rain that will have a pH value less than 7. But now the distilled water is a neutral solution that will give a pH value of 7. So they are neither acidic nor basic, and are now we are calling them to be neutral. So the pH values of bases range between 7 and 14. The pH values of bases range between 7 and 14. So solutions of ammonia, calcium hydroxide, and sodium hydrogen carbonate have the pH values between 7 and 10. They are now weak bases. They are weak bases. As the values increase from 7 to 14, that is also the way the strength of the bases increase. So you have solutions of wood ash, soap, and sodium hydroxide have pH values ranging from 10 to 14, and now we are saying that they are strong bases. So the pH scale is shown here. We have here a pH scale that now ranges from 0 to 14. So we are saying from 0 to values less than 4 we are saying they are strong acids. From 0 to values less than 4, they are strong acids, and they'll give either the red or orange color. So those substances will give either red or orange color using the universal indicators. Then weak acids range from less than 7, so between 4 and less than 7, and then they'll have a weak they'll have the strength of the acid will be weak, and they will give a yellow color. Then at exactly 7, we have the universal indicator with the solution used. If it is neutral, it will give a green color. It will give a green color, and that solution will be neutral. Then we have values more than 7 to values less than 10, that now will give a purple or will give a blue color, which now they are weak bases. Then you have those ones that now they are strong bases. They'll give either purple or violet color, that now they range from 10 to values less than to 14, 10 to 14. So that's how the pH scale, pH chart works. That's how the pH chart works. So after having obtained now the color, after having added the universal indicator, so now we look at using, we compare using the pH chart, where now we'll have the color and then the value of the acid or the base or the neutral, or if it is neutral, we now come up with the color and the strength of the solution, if it is basic, acidic, or neutral solution. So we go ahead and look at the properties of acids. Properties of acids. Properties of acid, to begin with the reaction of acid. Now looking at the reaction of acids with metals. So acids react with metals to give a salt and a gas. This gas is hydrogen gas. Now where this gas, the pressure of the gas is tested using a burning splint, where the burning splint now burns with a pop sound. Now the intensity of the pop sound depends with the amount of the gas produced and the purity of the gas itself. Amount of the gas and the purity of the gas itself. So you go ahead and continue to an experiment. We say that what happens when dilute acids come into contact with metals. So no, the experiment has not to be carried to each and every metal, because you have some metal that when they react with the acid, they are explosive, and also the metals themselves, they are dangerous to handle. They are dangerous to handle. So we go ahead with the experiment. We put a granule of zinc into 2 test tubes. We add 2 cubic centimeter of dilute hydrochloric acid to the first tube, and then we record our observation. We repeat the procedure using dilute sulfuric acid in place of dilute hydrochloric acid. So remember, we are having 2 test tubes. The one we have, in both we have zinc granule, and in one now we are adding hydrochloric acid, dilute hydrochloric acid, and the other one we are adding dilute sulfuric acid. So we say that we repeat the experiment using a clean magnesium ribbon. We also have a magnesium ribbon. We have aluminium foil. We have iron filings. We have lead and copper turnings instead of magnesium. So you go ahead and also we see how the dilute acids react with magnesium ribbon, aluminium foil, iron filings, lead and copper turnings instead of zinc. So you have a question, potassium, sodium and calcium should not be reacted with acid. Potassium, sodium and calcium should not be reacted with acid. These are some of the metals that explosively react with acid, so that they should not be reacted. So this is how now we now carry out the experiment, having a boiling tube with the zinc granules. We add dilute hydrochloric acid. After a reaction, after now the reaction has taken place, we remove the cork. Then we test the gas produced with a lighted splint or a burning splint, where it will burn with a pop sound. So we say that intensity of the pop sound depends on the amount of the gas produced and the purity of the gas produced. So we are saying that the intensity of the pop sound depends on the purity and the amount of the gas that is mixed with air that now has been produced, that now has gone ahead to mix with air. So when dilute acids are added to zinc, magnesium, aluminium, and iron, bubbles of a colorless gas are evolved. Bubbles of a colorless gas are evolved. So we'll see bubbles inside the acid that now we have used, that now that shows the reaction between the metal and the dilute acid. So the production of the bubbles of a gas is referred to as effervescence. So we refer to it as effervescence. So the gas produced is hydrogen gas. The gas produced is hydrogen gas. So the gas is tested using a burning splint. So the mixture of hydrogen and air burns with a pop sound. Where now you have said that the intensity of the pop sound depends on the amount of the gas produced and the purity. So this is a test for hydrogen gas. It is a test for hydrogen gas. So when dilute sulfuric acid is added to zinc granules, hydrogen gas and zinc sulfate are produced. Remember we said when acid react with metal, there is a production of salt and a hydrogen gas. There is a production of salt and a hydrogen gas. So the gas depends on the metal used. The gas depends on the metal used. So in this case, as we had zinc, so we'll have zinc either chloride or zinc sulfate, zinc chloride or zinc sulfate. So zinc zinc granules, they'll produce hydrogen gas and zinc sulfate, and the reaction can be represented using a word equation. So this is the word equation: zinc, which is a metal, reacting with sulfuric acid to give sulfuric acid and hydrogen gas. Now to give zinc sulfate and hydrogen gas. Now in this case, the zinc sulfate is the salt, and then hydrogen is the gas that is produced. Hydrogen is the gas produced. So similarly, zinc reacts to dilute hydrochloric acid to form zinc chloride and hydrogen gas. So it can also be represented with the word equation, where you have zinc reacting with hydrochloric acid, which is dilute, to give zinc chloride and hydrogen gas. So magnesium and aluminium reacts more vigorously with the acid than zinc. So magnesium and aluminium, they react more vigorously as compared to the reaction between the acid and the zinc. So aluminium, zinc, when we have magnesium reacting with the hydrochloric acid, we will have magnesium chloride and hydrogen gas. Aluminium reacting with hydrochloric acid, we will have aluminium chloride and hydrogen gas. So an acid can be defined as a compound that reacts with metal to form a salt and hydrogen gas as the only product. To form a salt and hydrogen gas as the only product. So metal reacted with acid will have metal salt and the hydrogen gas. So very reactive metals like potassium, sodium, and calcium react violently with acids. So the reaction of calcium with dilute sulfuric acid, slows down and eventually stops due to the formation of insoluble calcium sulfate. So now, while reacting now the calcium with sulfuric acid, the reaction stops. The reaction stops due to the formation of insoluble calcium sulfate. So the insoluble salt coats the metal and prevents further reaction. Also now we have lead reacts slowly with both hydrochloric and sulfuric acids, but each reaction eventually stops due to the formation of insoluble coating of lead chloride and lead sulfate respectively. Due to the formation of insoluble coating of lead chloride and lead sulfate respectively. So now calcium, the reaction stops due to formation of calcium sulfate that is insoluble. Also lead, the reaction stops when reacted with hydrochloric acid together with sulfuric acid due to the formation of lead sulfate and lead chloride. Then copper does not react with either dilute sulfuric acid or dilute hydrochloric acid. So the name of the salt can easily be derived from the name of the acid used as shown. Now the metal used, now it will give the name of the salt. The name of the salt. The metal used gives the name of the salt. So salts produce magnesium with different acids are here now. We have now the metal, our metal is magnesium. Then the dilute acids, we have hydrochloric acid, sulfuric acid, nitric acid, we have carbonic acid, we also have phosphoric acid. So with hydrochloric acid, magnesium will give magnesium chloride. With sulfuric acid, magnesium will give magnesium sulfate. With nitric acid reacting with magnesium will have magnesium nitrate. Carbonic acid will have reacting with magnesium will have magnesium nitrate. Carbonic acid reacting with magnesium will have magnesium carbonate. Phosphoric acid reacting with the with magnesium will have magnesium phosphate. We will have magnesium phosphate. Now we go ahead and look at the reaction of acids with carbonates and hydrogen carbonates. So an experiment how do dilute acids react with carbonates and hydrogen carbonates. How dilute acids react with carbonates and hydrogen carbonate. A procedure: we add a spatula full of sodium carbonate into a test tube containing about 5 cubic centimeters of dilute hydrochloric acid. Remember, now we are carrying an experiment of how carbonates and hydrogen carbonates reacts with dilute acids. Now here you are using dilute hydrochloric acid. So the setup of operator is as we are seeing that now we have sodium carbonate and hydrochloric acid that are reacting, are mounted on a clamp on stand, having that's inside a test tube. We have a cork, then we have a delivery tube from the test tube containing the sodium carbonate and hydrochloric acid to another test tube containing calcium hydroxide solution or lime water. So then we record the observation. So we repeat the procedure using different other dilute acids, that is sulfuric acid, have dilute nitric acid in place of dilute hydrochloric acid. Then you also record this the observation. So also apart from using the sodium carbonate, we also have calcium carbonate and sodium hydrogen carbonate in place of sodium carbonate. So action of acid on carbonate and hydrogen carbonate. So that's the reaction that now we are carrying out. So we go ahead and discuss the observation that we have made or we have seen. So when carbonates or hydrogen carbonates are added to dilute acids, effervescence occurs as the solid is used up. So a colorless gas is produced. And the colorless gas produced is carbon 4 oxide. So carbon 4 oxide is the gas produced, and when it is bubbled through lime water or the calcium hydroxide solution, a white precipitate is formed. So now how to test the carbon 4 oxide is by bubbling it through the lime water or calcium hydroxide solution, where now effervescence will be, where now a white precipitate is formed, but not effervescence. A white precipitate is formed. So this is the test for carbon 4 oxide. So the white precipitate is calcium carbonate. The white precipitate is calcium carbonate. So we note that if carbon 4 oxide gas is bubbled through calcium hydroxide for a long time, the white precipitate dissolves. So this due to the formation of soluble calcium hydrogen carbonate. This is due to the formation of the soluble calcium hydrogen carbonate. So acids react with carbonates and hydrogen carbonate to form a salt, water, and carbon dioxide. To form salt, water, and carbon dioxide. So the following word equations present some of the reaction between acid and carbonates or hydrogen carbonate. Between acid, carbonates, or hydrogen carbonate. So you have sodium carbonate reacting with hydrochloric acid. We have the sodium chloride is formed with water and carbon dioxide, because we said when now carbonate or hydrogen carbonate is reacted to dilute acid, now a salt is formed, water and carbon dioxide. Then you have calcium carbonate reacting with dilute nitric acid. We have calcium nitrate, have calcium nitrate plus water and carbon dioxide. When copper carbonate now reacts with dilute sulfuric acid, we have formation of copper sulfate, water and carbon dioxide. Also we have sodium hydrogen carbonate reacting with dilute hydrochloric acid. There is a formation of sodium chloride and water and carbon dioxide. So the general equations for the reaction of carbonates and hydrogen carbonates are: for the carbonates, dilute acid reacting with carbonate will have a salt, will have water and carbon dioxide. For a dilute acid reacting with hydrogen carbonate will have salt, water and carbon dioxide too. So the reaction between sulfuric acid and calcium carbonate stops after a short while due to the formation of an insoluble layer of calcium sulfate, which stops further reaction. So now when we react dilute sulfuric acid with calcium carbonate, the reaction stops due to the formation of an insoluble layer of calcium sulfate, due to a formation of an insoluble layer of calcium sulfate, which stops further reaction. So calcium carbonate reacting with sulfuric acid, there is formation of calcium sulfate, that is a solid, water and carbon dioxide. So let's now go further and look at the reaction of acids with bases. So acids with bases, they react. Acids and bases react to form. Acids and bases react to form a salt and water. Salt and water, and this reaction forms it's called neutralization reaction. So experiment: how do dilute acids react with bases? We have a procedure. We measure 10 cubic centimeter of dilute sodium hydroxide solution and put it in a clean conical flask. We add 2 to 3 drops of phenolphthalein indicator. We add dilute hydrochloric acid. Then we add dilute hydrochloric acid drop by drop while shaking the conical flask, and count the number of drops until the indicator just changes the color. So we repeat without adding the indicator. We add the same number of drops of hydrochloric acid to 10 cubic centimeter of dilute sodium hydroxide. So we put the resulting solution in an evaporating dish and heat the solution to saturate it. We heat the solution to saturate it. Then we allow the saturated solution to cool. Then we record our observation. Then we place a small sample of the calcium oxide into a test tube. We add to it 5 cubic centimeter of dilute nitric acid. Then we shake the mixture. So we repeat the procedure using also the following solids in different test tubes. We have zinc oxide, we have copper 2 oxide, we have magnesium oxide, lead 2 oxide, magnesium oxide and lead 2 oxide. Then we also record our observation. So instead we can also again replace the acid with dilute hydrochloric acid in place of dilute nitric acid. So we note that warming increases the rate of reaction between the reactants. Therefore, where a reaction does not seem to occur, the mixture can be warmed gently to encourage the reaction. So the reaction of acid with the bases. So let's now discuss and see now the observation that have been made. So phenolphthalein indicator is used to determine the endpoint of the reaction. Now the indicator is used to determine the quantity of acid needed to react with 10 cubic centimeter of dilute sodium hydroxide. So now we are saying that the indicator has been used to determine the endpoint of the reaction, and now the indicator is also used to determine the quantity of acid needed to react with 10 cubic centimeter of dilute sodium hydroxide. So it is not used in the next reaction to avoid contamination of the product. So that's why we say that when now we are carrying another reaction, we begin with new substances, also having clean apparatus. So the color of the phenolphthalein, say that is pink in basic solution. So at the end point, the color of the indicator in the solution turns from pink to colorless. So the endpoint is attained when one of the reactant has been used up. So when acid react with bases, they form a salt and water as the only product. They form salt and water as the only product. So we say that in the reaction between the acid and bases, there is a formation of a salt and water as the only product. So salt and water are all neutral products. Hence the reaction is referred to as neutralization reaction. So you say that a reaction between a base and an acid is a neutralization reaction, because now all the products that are being formed, they are neutral. They are neither acidic nor basic. So sodium hydroxide reacts with dilute hydrochloric acid to form sodium chloride and water only as the products. And now sodium chloride and water, they are all neutral. That's why you are saying that the reaction is a neutralization reaction. So the following are the word equation. So these are some of the reactions between the metal oxide and the acids. Remember now, metal oxide are bases. So calcium oxide and hydrochloric acid, we are forming a salt, which is calcium chloride and water. Zinc oxide and hydrochloric acid, that we have zinc chloride and water. We have magnesium oxide reacting with nitric acid, you have magnesium nitrate and water. We have lead 2 oxide reacting with nitric acid. We have lead nitrate and water, copper 2 oxide and sulfuric acid. We have copper sulfate and water. So a base is a substance which, when reacted with acids, forms salt and water as the only product. So that's the definition you can give to a base. A substance which, when reacted with acids, forms salt and water as the only product. So metal oxides, metal hydroxides, and ammonia solution are all bases. So metal oxide, hydroxide, and ammonium solution are bases. So the table below summarizes the properties of acids and bases. So let's begin looking at the properties of acids. Acids have a sour taste. They also have a pH value below 7. So remember, when we began, we say that some foods that you consume, they contain sour taste, and the presence of the sour taste is due to the presence of acids. So the sour taste is due to presence of acid. So they have pH values below 7. Then they turn litmus red, whether the solution or the blue litmus paper. Turns phenolphthalein indicator colorless. Turns methyl orange indicator pink. We have react with base to form salt and water only. Reacts with carbonates to form salt, water, and carbon dioxide, reacts with metal to produce a salt and hydrogen gas. So those are some of the properties of acids. Then let's look at those properties of base. They have a bitter taste. Even we say that foods that we consume, they contain bitter taste. Now the bitter taste is due to presence of bases. They have pH values above 7. They turn litmus either solution blue, or red litmus paper blue. They turn phenolphthalein indicator pink, turn methyl orange yellow. They react with acid to form salt and water only as the products. We go further and look at the effect of acids on substances. So industries emit several gases and waste products into the environment, leading to environmental pollution. So some of these gases dissolved in rainwater to form acid rain. This rain reacts with stonework, iron roofs, and other metallic surfaces, causing damage. So this effect is called corrosion. So corrosion is due to industries releasing some gases into air that now mix with the water to form acid rain, where now acid rain have effect on metallic surfaces that now cause damage. Where the damage is corrosion. When these acidic gases in the atmosphere are inhaled, they also cause respiratory disorders. So soil also may become acidic due to the leaching and waterlogging. Such soil is unsuitable for growth of many plants. So remember, when you have acid rain, makes the soil to become acidic. So due to the leaching and waterlogging, then it makes the soil unsuitable for growth of many plants. So we go ahead and look at the application of acids and bases now in real life, how now they are useful to us. We begin with the uses of acids. So carbonic acid is used in aerated drinks to enhance taste. As we say that, we know that we have carbon dioxide that now preserves the drinks. Now carbonic acid is used to preserve the taste, or to enhance the taste. Then we have hydrochloric acid that is used to clean metal surfaces. So for the cleaning of metal surfaces, hydrochloric acid is used. Sulfuric acid is used in car batteries. You have manufacture of fertilizers, you have etching of metals, you have manufacture of paints and detergents. So sulfuric acid is also useful in car batteries, manufacture of fertilizer, have etching of metals, have manufacture of paints and detergents. Then we have also nitric acid that is used in the manufacture of dyes, you have paints, explosives, and also fertilizers. Looking at ethanoic acid and citric acid are used as flavors in food. Ethanoic acid and citric acid are used as flavors in food. So those are some of the uses of acids. Then let's look at now the base. Magnesium oxide and hydroxide, they are used in the manufacture of the anti-acid tablets and also lining of furnaces. Calcium oxide and hydroxide, they are used in neutralizing soil acidity and industrial waste. So when now soil becomes acidic, it is neutralized with calcium oxide and hydroxide. Also the industrial waste that now that contain acid, it can be neutralized using calcium oxide or hydroxide before they are now emitted into the soil or into the environment. So it is also used in making cement and concrete. It is also used in manufacture of toothpaste. Calcium oxide and hydroxide is used in manufacture of toothpaste. So you can see that they play a bigger role in our real life. We have sodium hydroxide that is used in manufacture of soap. and also as a decreasing agent. Is also a decreasing agent. So it can be used as it is an agent of greasing. It is a degreasing agent. Degreasing agent. It removes some stains of grease. So then you have ammonium solution, which is also used as a degreasing agent. It can remove stains of grease. We have manufacture of fertilizer. We have manufacture of nitric acid. We have manufacture of nitric acid.